So where we finished up on our last video is we were talking about characteristics of waves. Okay. So we've got our characteristics of waves. One is that we said they carry energy. Mechanical waves have to have a medium. And we talked about that we could have a transverse wave. And that's one that looks like a wave on a string that's going to go like this. And we also talked about a longitudinal wave. And our longitudinal wave, we said, the best thing to demonstrate that is with a slinky. And that would give us that we would get a real dense area, and then it wouldn't be quite so dense, and then we get a real dense area, and it wouldn't be quite so dense, and we get a real dense area, and it wouldn't be quite so dense, and we get another real dense area. So we can look at that. And we use this idea of compression. And you can look at this as rarefaction or rarefication, where it's going to be thinner and it's going to come up and be denser. So if you think about a tuning fork, so we got a tuning fork, and as my tuning fork vibrates, you're going to get an area where it's going to affect the air particles around it, and we'll get less dense, and we'll get more dense, and we'll get less dense, and we'll get more dense, and we'll get less dense, and we'll get more dense as these things vibrate back and forth. We know that this is impacting the air around it. And if we think of a speaker, and if you ever look at how a speaker works, there's this part that vibrates in the middle, it vibrates back and forth. So it's going to do the same thing. We're going to get that puff of air that's going to come out and do the same thing. So sound waves, they're going to be mechanical waves. So they're going to have a medium, and and you guys have seen this happen before. I'm sure somewhere along the line you've seen the bell jar trick where we have a alarm clock and you see the little thing ringing back, and you have the vacuum bell jar, and once it's in the vacuum, we don't hear sound anymore. Initially, you'd hear the sound, and as they pull the vacuum out, we don't get sound anymore, because a sound wave has got to travel through a medium where we're going to get this compression and rarefaction. We're going to get those characteristics of that material. The other thing that we know is, just like with our vacuum and our bell jar, we know that sound, if I have a rail, I can put my ear on the rail and I can hear something down the metal rail, but before I can hear it in air. And that, again, is because we have a different material that we're dealing with. We have a totally different material. And when I lived in Utah, if you had an earthquake happen up in Yellowstone, the sound would travel through the mountains, and you could actually get the sound of that earthquake in your house. You wouldn't feel it, but you could actually hear it. So you can get those things. So we also also saw at the end of yesterday that the velocity of sound is going to be the wavelength times the frequency. So let's draw our wave here. So we're going to represent with our simple harmonic motion. If I do this in terms of distance, so this is distance, the wavelength is one complete cycle. That would be my wavelength. Frequency is related to time. So my wavelength is going to be the length, and my frequency is going to be my time, and we have our velocity is wavelength times frequency. And we were talking about that, and this is a general for any wave.
And is that time just what that length, the wavelength is?
Yeah, that's the period. So if I do this in terms of X, that, and my frequency is one complete cycle. So this is general for any wave, and it can be a mechanical wave or an electromagnetic wave. Doesn't have to go through a medium, but we're going to see that mechanical waves, the speed of a mechanical wave is actually going to be dependent. You can look at it with this, where B and rho, where B is the bulk modulus and rho is the density. Because we know that sound, the speed of sound, so if I do the speed of sound, the speed of sound in water is 1,493 meters per second. Speed of sound in air is roughly 331 meters per second. And this is because water and air have different properties. And air is going to have different properties yet. In fact, the speed of sound in air is going to be temperature dependent. And you may see this under a couple of different methods. So temperature in Kelvin, 331 meters per second is going to be, and you get that because, and again, what's happening in air is my bulk modulus is going to respond differently, and the density of air is going to be different depending upon my temperature. And it also depends on humidity, because we all know, and we've experienced, if you go outside on a foggy morning, sound travels differently than if you're out in the desert on a very dry area. Moisture is going to cause a difference in our sound. And basically, if we look at our velocity here, this is really the square root of our elastic property divided by our inertial property. How much inertia does it take, to overcome to get our little molecules moving? So sound is going to be dependent on our medium. It is a mechanical wave. It's still going to carry energy, and we know that. We know that it's going to carry energy. Hang on, I got someone in chat. Warren Houston, you're right. So, and we know that sound travels differently underwater, sound travels differently in wood, sound travels differently in rock. We know that's there. And if you've ever been to a concert, or you're standing in front of a speaker, or you're next to somebody's car who's sharing their music with you, you can feel that energy from that speaker. You know you're going to feel the energy, so it's pretty easy to understand that sound does deal with that energy. So it really works with that part of what's going on. So let's talk about sound has certain properties. So if we think about sound, we use the terms ultrasonic, infrasonic, audible, and probably misspelled it. This is related to human hearing. This is below. If I'm dealing with infrasonic, I'm dealing with sound that's in frequencies below what the human ear can hear. If I'm dealing with ultrasonic, we're dealing with sounds that are above what the human ear can hear. And we'll talk a little bit more about that tomorrow. We'll also talk a little bit more about what we refer to as loudness, timbre, and pitch. Pitch is related to frequency. So if we're talking about what the human ear will hear, pitch will be like high C or low C. It's going to be related to frequency. Loudness is related to intensity. And that's what we're about to talk about. Now, timbre is a little bit different. We can look at timbre and we can describe this as color. Timbre is what gives us the difference between if I have an A, a music note A, and it's played by a violin, it's going to sound differently than that same music note A that's played by a piano, or that same music note A that's played by an oboe. And that relates to the timbre because we don't necessarily just hit perfect notes. And our resonant boxes, the violin, the resonance box of the piano, the resonance tube of your oboe, are going to add different overtones, different undertones, different things that are going to be there. And that's going to allow us to tell the difference between a guitar, a violin, a bass, a stand-up bass. You're going to see that differently. So you're going to get those. So we use these terms to help describe sound. But we want to talk about intensity. So let's talk about what happens for sound. So I'm going to have a sound generator here. So I've got my speaker or my little object here is a sound. When it vibrates, it's going to send out a wavefront. And it's going to go out in a spherical fashion. Okay, it's going to go out in a spherical fashion. And we can draw our wavefronts. We can use arrows to draw our wavefronts because we can play Miss Frizzle. And the further away I am, I may be looking at my little perpendicular wavefront here. And it may look like my sound is just coming directly at me. But if I'm doing one frequency, it's going to send out a pulse. And as that pulse moves away, look what's happening to it. As I'm moving away, I'm going out a distance R away, and things are happening a little differently. So if we think of intensity, we actually define our intensity as, we're going to use I for intensity. And we're going to define it as we go out, our area of our sphere expands. The surface area of our wavefront is going to expand. And it's going to be a change in energy divided by a change in time. And if you think about it, if you're next to the speaker at a rock concert, it hurts if you're standing right up there because it's that energy is really intense as I'm right up against my speaker. But as I move further and further away, we're okay. If I'm dealing with OSHA regulations, if they say if you have to elevate your voice next to an object, you're exceeding the recommended heating or hearing level of what you're supposed to be, and they ask you to step away so that you're further outside that radius. Because what's going to happen here, and just as a reminder, we've seen this before, that's power. Energy over time is defined by power. But if I'm looking at my area and I look at the surface area of a sphere, that's 1 over r squared. And I've got my change in energy over change in time. So I can have this as power divided by area. And it's going to go as power divided by 4 pi r squared. So as my intensity, as I move away from my source, it's going to fall off as 1 over r squared. So if I plot this, and this is what you're gonna actually do this. So I have a source. So this will be a source. And think of this source as an air conditioner. It could be a tractor. It could be a frequency generator on your computer. I would recommend doing this outside because you're going to get better results outside than you're going to be in the house, because what happens is if my wave hits a wall, it's going to reflect and I'm going to get interference. So you're better off doing this, and I would recommend like going ahead and using when your air conditioner's running outside. You're on your cell phone. You can do this in Firefox, or if you want, there are a number of free apps. So let's look at Firefox first. Firefox, you can do an audio scope or an audio amplitude, get the magnitude of the sound. Or you can get your audio scope. You can get a lot of those different things that are there. You also have a tone generator on your Firefox. Or you can get a sound meter. And these are free. You can get them in the App Store, either for your, this one wants to update. It's been a little while since I've updated it. Give it just a second here. There we go. Okay. This one I have actually checked with an actual industrial hygiene sound detector. It works really, really well. It judges it. You can see that the decibels are changing, and we're going to talk about decibels here shortly. And we're going to convert between decibels and intensity in just a second. But you can actually go out and measure what you're dealing with for your source. And you can't go right up against your source, but you can use your sound meter to get there. But you'll say start like 1 meter away. And then you're going to measure your intensity as you move, say, 2 meters away. And then 3 meters. And you should end up with a graph that goes as 1 over r squared. It'll actually fall off as 1 over r squared. And the reason it's going to do that is because look what's happening to my sphere as I'm going further and further out from my item. So that's what the experiment is. The data is fairly easy to gather. It's just that you're going to have to find a source, noisy source, and measure some distances out and take your intensity readings. Now, your intensity readings can be done in intensity or in decibels, and we're about to talk about decibels. Part of our problem is that hearing, so let's look at human hearing. So we talked that intensity is equal to power divided by area, which we can look at as power divided by 4 pi r squared. The loudest sound we can hear, and this is our tolerable, is 1 times 10 to the 12th watts or Webers. It's watts per square meter. The faintest sound or what we call the threshold of hearing is 1 times 10 to the minus 12 Weber meter or watts meter squared. Okay. Our human hearing has significant ranges, huge ranges, absolute huge ranges. So that's why we measure in decibels, because we are dealing with several orders of magnitude. So a decibel, we give it a script or a Greek bead. And we say that that's defined as the logarithm of the intensity of the sound divided by the threshold of hearing. Okay, we get that. So let's look at, we've got an intensity level. We could have a grinding machine. Has an intensity level of 1 times 10 to the 5th, the minus 5th watts meter squared. If I want to find my decibel level, oops, I forgot a 10. We put a 10 in front. My apologies. Is going to equal 10 times the log of 1 times 10 to the minus 5 divided by 1 times 10 to the minus 12. And if I do that and I plug that into the calculator, this is going to be giving me 10 log 1 times 10 to the 7th. I take that. This is going to be 10, 7. This is going to give me 70 decibels. And usually we write decibels with that particular item. So you can calculate those decibels. Now, let's look at, because sound is very unique, and we want to work with our logarithms for a little bit. If I have one trumpet and it's at, let's go ahead and Let's do, oh, we'll do a vacuum cleaner. We'll do one vacuum cleaner. And it has an average of about 70 decibels. And we're going to go in and we're going to hurry up and we're going to clean a big space, and we're going to end up having 5 vacuum cleaners. We want to know what the new decibels are for 5 vacuums. We just can't add 75 times. That's not going to work for us. So what we do is this. My log, well, first of all, let's find the intensity of one vacuum. And that's going to be 70 decibels is equal to 10 log our intensity divided by our threshold of hearing. So we're going to get 70 divided by 10 is going to equal the log of what we're looking for divided by 1 times 10 to the minus 12. Okay. So now I get 7 log I 1 times 10 to the minus 12. I'm going to get 10 to the 7th is equal to I divided by 1 times 10 to the minus 12. So I'm going to get 1 times 10 to the minus 12 times 1 times 10 to the 7th is equal to our intensity. So we're going to get that. And that's going to be 1 times 10 to the 5th. Is equal to our intensity. So you can get, so we figured out our intensity, but now we want to do 5 vacuums. Well, if I want to do 5 vacuums, what we've got are some rules. So our log rules are the log of AB is going to equal the log of A plus the log of B. The log of A divided by B is equal to the log of A minus the log of B. And the log of A to the N is going to equal N log A. So we want to know the new decibel level. So our new decibel level is going to be 10 log. And now I'm going to have 5 vacuums times my intensity divided by my threshold of hearing. This is going to be 10 times. We're going to have the log of I divided by I0 plus the log of 5. We already know what this is because we already figured that one out. This is going to be 7. Because that came from our previous one. So I get 10, 7, and my log of 5 is 0.6989, or we can go ahead and say that that's 0.7. So I get 10, 7.7. My new log is going to be 77 decibels. So it does behave a little differently. And the reason it behaves a little differently is because of this huge range that we have in our hearing. So we have to use some other scientific function in order to get us there. We have to be able to expand on that. And that gets us our information there. So we can look at, again, our intensity is going to equal our power average, 4 pi r squared. So we can actually do comparisons of our sound, and you are actually going to do this and look at that particular aspect as part of your lab. I recommend looking at example 14.3, because that will help you with your laboratory. And then section 14.5 will draw the wave fronts a little better than I can here. And you can also look at the PowerPoint that I have, because the PowerPoint actually uses those drawings as well. So that gets us halfway through, or actually more than halfway through chapter 14. When we come back tomorrow, we'll talk about the Doppler effect, and you will have a Doppler effect laboratory, or a Doppler effect activity. That's going to be more of an activity than it will be a laboratory, but you'll have a Doppler effect activity to do for next week as part of our labs, our lab grade. And then we'll talk about standing waves and those kinds of things tomorrow. So questions, concerns?